Welcome! If you're studying microbiology or you're just fascinated by how we fight off disease, you are in exactly the right place. We're about to take a deep dive into the incredible story of vaccines, one of modern medicine's absolute greatest triumphs. So let's kick things off with a pretty weird question. Why on earth were people back in the 1800s convinced that a new medical treatment would make them sprout cow heads? I know it sounds ridiculous, but this is the very beginning of our story. And the answer tells you everything about just how desperate people were. To really get that fear and the unbelievable relief that came after, we've got to rewind. We need to go back to a time when diseases like smallpox weren't just a threat, they were a terrifying, and for so many people, a totally unavoidable part of life. People were so desperate that they turned to this really risky practice called variolation. I mean, think about this. You'd take gunk from a sick person and deliberately infect a healthy one, just praying they'd get a mild case. It was a huge gamble. Yeah, it often worked, but it could also cause a full-blown, fatal infection. There had to be a better way. And that better way, that breakthrough that changed everything, well, it came from a pretty unlikely source, the humble cow. So this English physician, Edward Jenner, he had a keen eye. In the late 1700s, he noticed something fascinating. Milkmaids who got this mild disease called cowpox just didn't seem to get deadly smallpox, ever. That connection was the absolute game changer, offering a much safer way to get immunity. Jenner's big discovery in 1796 really kicked off a golden age of innovation. I mean, look at this timeline. Over the next 150 years, scientists just built on his work, one breakthrough after another, knocking down some of humanity's most feared diseases, from rabies in 1885 all the way to polio in 1955. And here are the two giants who really defined that era. On the left, you've got Jenner, the brilliant observer who saw a pattern in the world around him. And on the right, Louis Pasteur, the scientist who took it a step further. He established the principle of attenuation, the idea that you can actually weaken a pathogen in the lab to make it safe, but still able to train the immune system. That's the leap from just observing to actively engineering a solution. Pasteur's work basically opened up a whole new toolkit for fighting disease. It gave us an entire arsenal of different vaccine technologies. So let's take a look at what we've got in that arsenal. First up, we have live attenuated vaccines. Okay, so what does that mean? Basically, they contain a live version of the virus or bacteria, but it's been weakened, attenuated, so it can't cause serious disease. Think of it like a training simulation for your immune system. You get to fight a sparring partner, not the heavyweight champ. So here's how it works. That weakened virus can still replicate a little bit, just enough to get the attention of your immune cells, especially these guys called antigen-presenting cells. That's all it takes to kick off a full-blown immune response and, crucially, create that long-term immunological memory, all without you ever having to get truly sick. Okay, so here's the deal, right? There's always a trade-off. The huge pro is that you get this incredibly strong, long-lasting immunity that's a lot like what you get from a real infection. But the con is a big one. Because the pathogen is technically still alive, these vaccines aren't safe for people with weakened immune systems. But scientists didn't stop there, of course. They got even cleverer. The next logical step was to use a completely killed or inactivated pathogen. Way safer. Then, technology let us get even more specific, using just tiny pieces of the pathogen, which we call subunits. And now, in the modern era, we can use something like mRNA to just deliver the genetic recipe so our own cells can make a tiny, harmless piece of the enemy. But here's the thing, and this is so important. No matter the tech, whether it's an old-school killed virus or a cutting-edge mRNA vaccine, they all have the exact same goal. Every single one is designed to do one thing: present a piece of the bad guy called an antigen to our immune system's frontline soldiers, the antigen-presenting cells. All right, so the antigen is in. What happens now? How does a vaccine actually teach your body to remember an invader? Not just for a few weeks, but for years, maybe even for your whole life. It all kicks off with those antigen-presenting cells, the APCs. You can think of them like the immune system's scouts. They find the antigen, gobble it up, and then they march it over to a lymph node to show it to the generals of the immune army, the T cells. Once those T cells see the threat, they sound the alarm. They activate another kind of soldier, the B cells. And these B cells are amazing. They transform into two critical units: First, you get plasma cells, which become these incredible antibody factories, just churning out proteins to neutralize the enemy. And second, you get a whole army of long-lasting memory B cells, which will stand guard for years to come. And this is why your response to a booster shot, or to the real infection, is so much faster and stronger. That first dose, the primary response, takes a while, like 5 to 10 days, to build up your defenses. But the second time around, those memory cells are already there, locked and loaded. They slash the response time to just 1 to 3 days and pump out way more antibodies. It's an incredible system. So, we've gone deep into the science. But what's the actual payoff? Why does understanding all this immunology matter in the real world? Well, to see that, we've got to zoom way out and look at the global picture. The impact is, well, it's just staggering. Every single year, vaccination programs save an estimated 3 million lives. Let that sink in. 3 million people, mostly kids, who get to live and grow up because of the immunological memory we were just talking about. And this right here, this is probably our single greatest public health victory ever. The complete and total eradication of smallpox, a disease that had haunted humanity for millennia, was systematically hunted down by a global vaccination campaign until, in 1980, it was gone, wiped from the face of the earth forever. The win against smallpox gave us a clear playbook. And for any of you studying microbiology, these definitions are absolutely key. The ultimate prize is eradication. The pathogen is gone from the entire planet. But regional elimination, like what we've done with polio in most of the world, is still a massive win. And even control, getting a disease like tetanus down to the point where it's no longer a major threat, is a monumental achievement. And the pace of all this is just accelerating like crazy. The virus behind COVID-19 was identified and sequenced in January 2020. The first approved vaccines were going into arms by December of that same year. A process that used to take decades, even centuries, is now happening in months. It's just incredible. You know, the journey from Jenner's simple observation about milkmaids to the rapid, worldwide deployment of custom-designed mRNA vaccines, it's just an amazing testament to what science can do. It really leaves you with one final thought. Now that we can essentially program immunity, what's next? Vaccines for cancer, for allergies, for autoimmune diseases? The next huge breakthrough is probably a lot closer than we think.